Hello, in this video, we're going to cover the divergence theorem. Let's start with, suppose we have a vector field that defines a vector at every point in R3. Suppose S, so suppose S defines a surface, a closed surface, with positive orientation. And by that, we mean that it has outward pointing normal vectors. And that it surrounds the solid region E. Let's go through and draw a picture so that that's crystal clear what we mean by that. So we can imagine something like a sphere, that's been smashed up a little bit. That's what that picture is supposed to represent. So it has a clear top, bottom, front, back, left, and right. Okay, so there's no opening to the object. It's completely enclosed. Okay, and then so we would say that the outer piece is the surface S, and then the inner part is E. That's the region that's inside the surface. All right, so what does the divergence theorem say? It says that if we went through and found f dot ds, which is the flux, that would equal the triple integral, which is the divergence. Okay, so we've got on the left side, we've got the double integral of f dot ds. That's a flux integral. So that's finding the flow across the boundary of the surface. And then on the right side, we have a triple integral of the divergence of f across object E. So what is this saying? What is the divergence theorem? Let's go through and analyze each side of this just to translate it. So that we can understand what it's getting at here. All right, so on the left-hand side, we have this f dot ds across the surface S. So this gives us a measure of flux. And by flux, we mean a flow across the surface. Okay, so the idea here is that the ds here, if you were to represent that, if we put some normal vectors on here, what f dot ds calculates is it calculates the degree to which f, which is the vector field vector, it points in the same direction as ds, which if you break this down, you can rewrite this as this is f dot n ds. And so this finds the degree to which the vector field vectors point in the same direction as the n, which is saying how much do the f from the vectors point across the surface? How much flow is there from the vector F across the surface. That's what this calculates. Okay, so the left-hand side is about measuring the flux across the surface. Then the right-hand side, we have divergence of F. And what this gives us, so we know what the divergence does. The divergence measures how much spread there is as a point. So this is a measure of the spread at all of the points inside. Okay, and so the idea is that you go to each point inside here and you calculate how much spread occurs at that point, how much, if there were, if you could imagine leaves sitting in this, contained in this three-dimensional picture, and then you went through and calculated how much those leaves spread out, at any given point. If you calculate the spread at all of the points inside, then that would give you the right-hand side. Okay, and so what the divergence theorem says is that these two things are equal. If you go there and you think about that, it's not that far-fetched. If you imagine going to all of the points inside of here and calculate how much those points have spread type behavior, how much they're spreading apart of the stuff that's in the vector field. Are they expanding? Is there expansion going on? If you calculate all the inside of here, and there's a significant amount of expansion going on inside of the object, then it stands to reason that there would be expansion along the outer edge, and vice versa. If at every point you have a negative divergence, so that the vector field is showing a contractual type behavior, then you would imagine that you'd get a negative flux, as if everything inside of here is contracting, then you're pulling things in from outside of the object through that surface, inside. And so if stuff is being pulled inside, then that's pointing in the opposite direction of the normal vectors, and so you'd end up with a negative flux. Okay, and so if you think about spreading or contracting for points that are inside the object, then it does make sense that that would affect what's going to happen on the outer edge of the object. So on the surface, the theorem there's some reason to believe that it does make sense. Okay, so let's go there and take a closer look and prove to ourselves that it is true. All right, so let's start with a picture. All right, and so if we're going to go through and prove this to ourselves, what we can do is we can start off by picking an object inside of here to work with, similar to what we did with the Green's theorem and Stokes' theorem. All right, and the object in this case we're going to start with a cube. All right, so let's take that object and just take it out to the outside, and let's blow it up. What we're going to do with that cube is we're going to go through and we're going to find the flux across the edges for just that cube. Okay, so what would that be? So we're going to find how does the vector field point downward out of the bottom? Does the vector field point upward out of the top? Does it point to the right, on the right side, left on the left side, and forward on the front and backward on the back. So we're going to go through and we're going to do the calculations for these. To do that, we'll go through and we'll label some of the points on here. We're going to label this as x, y, x sub I, y sub j, z sub k. Okay, and then so this point here, we would get x sub I plus change in x, y sub I, z sub y sub j. Oh, wait, hold on. Oops, sorry. Sorry. This point back here is x sub I, y sub j. My apologies. This point is x sub I, y sub j, z sub k. And then this point is the one where you're adding the change in x, y sub j, z sub k, and hold on, and so on. And you can go through and figure out the rest. This one's you're going to add the y coordinate. So you're going to add change of y. This guy here, we would add the z coordinate, x sub I, y sub j, z sub k plus change in z, and so on. You can figure out what the other points are as necessary. All right, so if we're going to go through and find how the vector field points out of the bottom, what we can do is we can take f, right, at this spot here. We're going to find the vector field vector. So that would be f at x sub I, y sub j, z sub k. And what we can do is we're going to go through and we're going to dot product it with negative k. Why is that? It's because we're trying to find the degree to which the vector field points downward at this point. Okay, so if it points downward, then we're going to get we would get a positive value from the dot product here between these, because this one would have a negative k, this one would have a negative k, and then they would combine to give us a positive value. All right, so what we're doing is we're taking the vector from the vector field there, and we're dotting it with this vector to figure out the degree to which the vector field points downward out of the bottom. Okay, so to take into account the size of the bottom, we're going to go through and we're going to multiply this by change in x, change in y. And that's because this distance is change in x and this distance is change in y. So the area for this bottom is given by that. And then we can go through and actually do the dot product here if we represent f and we say f equals p I plus q j plus r k. So if we actually went through and did this dot product, what would happen? So f is these three, and you're just going to end up dot producting the rk with the negative k, and so we're going to get negative r, and specifically at x sub I, y sub j, z sub k. Now, what about the top, right? So we can go through and do the top. For the top calculation, we want to go through and use this point here. You can use, we're going to pick this one, you know, for going through and doing the proof here, because it has just the right behavior that we want. But similar to the Green's theorem, we're assuming that this cube is small enough that we have consistent behavior across the entire top, not just at this point, but at all 4 points. And so if we went through and did that, we'd have x sub I, y sub j, this is z sub k plus change in z. Okay, so that's this point right here. And then we're going to dot product that with, for the top is positive k. We still have change in x, change in y, oops, for the size. And if you go through and multiply that out, you're going to get positive r. It's at x sub I, y sub j, z sub k plus change in z. Okay. And so we can go through and do some similar stuff with the back and the front and the left and the right. If you do that, you're going to get f of x sub I, y sub j, z sub k dotted with, and we've got that one should be a negative I, change in x. Let's see, hold on here. So this one is for the back. This was, let's just go ahead and label these. This is the bottom. This is the top. This one's the back. The back is here, and that should be change in y, change in z. And if you go ahead and dot product those, you're going to get q, negative q at x sub I, y sub j, z sub k. And then for the front, we'll do f, x sub I plus change in x, y sub j, z sub k, dotted with I, change in y, change in z. We get positive q, x sub I plus change in x, y sub j, z sub k. And then it's similar for the right and left. You can just extrapolate those. So what are we going to do with these, right? So once you go through and find the degree to which the vector field points down, so that's going to be the bottom flow, top flow, back flow, front flow, left flow, right flow, we go through and we add all of them up. Okay, so we can add all of these up. And when we do that, we're going to go through and group them by R, Q, and those are supposed to be P's, not Q's. P, Q, and R. All right, so what does that look like when that happens? We're going to get R of x sub I, y sub j, z sub k plus change in z minus R of x sub I, y sub j, z sub k. And then we got P of x sub I plus change in x, y sub j, z sub k, minus P of x sub I, y sub j, z sub k. And then the other one we got is Q, x sub I, y sub j plus change in y, z sub k, minus Q, x sub I, y sub j, z sub k. Okay, so going back to our partial derivative definition, what can we say about this? Well, let's just kind of do a little off to the side calculation here, right? So we know that R of x sub I, y sub j, z sub k plus change in z minus R of x sub I, y sub j, z sub k over change in z, if you take the limit as change in z goes to 0, we know that this equals R, partial of R with respect to z. Okay, so what we can say there is if we get rid of this limit part, we can say that these are approximately equal. And then we can also go through and then move the change in z over to the other side. And so we'll get R of x sub I, y sub j, z sub k plus change in z minus R of x sub I, y sub j, z sub k is approximately equal to the partial of R with respect to z times change in z. Okay, and so what we can do is we can go through and just pop this into our definition here above. So we're going to get approximately equal to partial of R with respect to z. Okay, whoop, I forgot something here. There's something missing. Okay, hold on. This, we forgot our change in x, change in y here. Or I forgot our change in x, change in y. And this one should have change in y, change in z. And you can see that if you go through and calculate the dot product of this with this, that gets you the R. There's the negative. And so what about this guy? It should be right there. And we need it. That's why I'm like getting to this point where I'm like a little confused. I'm like, wait, where did that piece go? We need that other piece. Okay. So this should all be, let's do this. This is probably the easiest way to do it. We can go through and just say we have this times change in x, change in y. This times change in y, change in z. And this times change in x, change in z. And now we can go through and say this is going to be approximately equal to. So this part here becomes this. So we're going to have partial of r with respect to z, change in z, and then we've got a change in x, change in y. You can do the same thing with this guy. This is going to be approximately equal to the partial of p with respect to x, change in x, and then you've got the change in y, change in z. And then this one is going to be approximately equal to the partial of q with respect to y, change in y, times change in x, change in z. And if you put all of them together, since we're adding here, we can put all of them together. And what happens here, you get partial of r with respect to z plus the partial of p with respect to x plus the partial of q with respect to y, change in x, change in y, change in z. And what is that? That is the divergence of f times change in x, change in y, change in z. Okay, so what does that mean? Well, what we were finding is we were finding the flux. We were finding the degree to which the vector field points across the edges for this cube. And it turns out that the flux for a small cube is the same thing as calculating how much spread there is for that small cube. So this is the spread. If you think about that, that kind of does make sense. Though the notion of spreading out would be how much flow there is across, how much flow there is away from a point. Like if you said that's the center point, how much spread there is at that point would be how much the vectors point away from that point. So the idea of spread, which is our definition for divergence, and the idea of flux across a cube, those are the same. Okay, and then so the cool thing is that once you realize that, you can go through and use that fact to basically establish the divergence theorem. So how do we do that? Let's try and draw a very big picture. Here's our closed surface. Okay, and so what we can do is we can go through and we can put cubes inside of here. Let's just put a cube in here. Right, and we know that the calculation here for the flux there is given by divergence of f, change in x, change in y, change in z, summation, limit. All right, so we've got I going from 1 to n, j going from 1 to m, k from 1 to o, and then we're taking the limit as m, n, and o go to infinity. So what this would represent is it represents this cube, and then these summations move the cube all around inside of here. And so we end up going through, we end up getting the triple integral divergence of f dv over e. All right, so this calculation is what we end up getting for going through and calculating the flux, right? The flux, the degree to which the vectors point outside our cube. right? If we go through and move that cube around where we're calculating the flux, you move that cube around inside of here, you're going to end up getting this. Okay, so that's one side. Now, what about the other side? All right, so actually I'm gonna need to draw the cube even bigger. Let me redraw it. I still made it too small. We need it pretty big to be able to see what's happening. All right, so there's our cube. Here's our vectors. So we're finding the leftward flow, the rightward, topward, bottomward, frontward, and backward. You're finding the flow out of all of the sides. You're just going through and doing that by moving this around inside of our object. That gets us the triple integral. Now, what if we actually do that? If we actually go through and draw the cubes, draw the other pictures, what's going to happen as we do that? So what if I were to go through and draw a cube above this one? Okay, if I do that, right, that's the picture I get. And then if I go through and draw the arrows on it, so this points to the left, right, front, back, upward, and downward. And look at that. We've got this wall here. See how it's got an upward arrow and a downward arrow? That means that one of them is going to be positive and the other one's going to be negative, and otherwise their values are the same. And so this wall cancels out when we actually go through and start adding up the cubes. What if I put a cube to the right side here? All right, so we get an upward arrow, right, left, down, front, back. And you can see this wall here, we've got a leftward arrow and a rightward arrow, so that wall cancels. Okay, and so if you keep going through and doing this, you could put a cube here, and then this wall is going to cancel, this wall is going to cancel. As you go through and put more and more cubes around this, the inner walls all cancel. Inner walls all cancel as you put cubes in here. Actually do the actual calculation. And if all of the inner walls cancel, what's left? If all of the inner walls cancel, the only thing that's going to be left is just the parts of the flux that are pointing, just the parts that are on the exterior, just the parts that are pointing outside. Okay, and that is going to end up being f dot ds across the surface. So in the end, we're just going to end up getting these outer pointing normal vectors, so the outer pointing vectors when everything inside ends up canceling. And the outer pointing vectors, if you just have those, that is the calculation of the flux across the surface. So everything on the inside ends up canceling out. All right, and so this is the two different cases. So in one case, we just go through and you just go ahead and write out the divergence. You do a cube in there and you say, you know what, if I went through and moved all around, I would end up getting the triple integral of the spread at every point. And on the other case, you say, oh, wait, if I actually do the calculations, all the inner stuff cancels, and then I end up getting the surface integral instead. And so that's why these two are equal, because you end up getting the same thing for going through and doing the calculation two different ways. All right, examples. So let's go through and do a couple examples. So the instructions here are to use the divergence theorem to calculate f dot ds over the surface. Okay, and so we've covered this in the video on Green's and Stokes. If they ask you to go through and use the divergence theorem, if they say use the divergence theorem to calculate this, they don't mean to go through and calculate this directly. They're telling you to use the divergence theorem to calculate the integral of f dot ds. They mean to use the fact that this equals the triple integral. So they want you to calculate the triple integral. And so that's what we're going to do here. We're going to calculate the triple integral side to go through and find the double integral side. All right, so the instructions are to use the divergence theorem to calculate this. They go through and they give us that f equals xy e to the z I plus xy squared z cubed j minus y e to the z k. And they also give us the surface. S is the surface of the box bounded by coordinate planes and x equals 1, y equals 1, and z equals 1. All right. So you can draw yourself a quick little picture. That frequently is helpful. We've got a box, coordinate planes bounded, and then x equals 1. So you've got 1, y equals 1, there's 1. And then z equals 1. There's our box. So it's just a big cube. All right. And they want us to go through and use the divergence theorem to calculate this. So to do that, first we need to go through and find the divergence of f. So you take the derivative with respect to x of this first part, that's y e to the z. Take the derivative with respect to y of the second part, that's going to be 2xyz cubed. And then take the derivative of this third part with respect to z, that's going to be minus y e to the z. And look at that, this nice stuff happens, and we get 2xyz to the third. All right, and then so now we want to go through and do our triple integral. That's what we're calculating is the triple integral of the divergence. So just pop the divergence in there. And then we've got dv over our object E. All right, so we need to choose an order of integration for our cube. Since the sides are all constant, or all flat like that, we can go through and do a triple integral. We can do the triple integral just with very simple bounds. We can go 0 to 1, 0 to 1, 0 to 1, and the order of integration doesn't matter. So let's just do that. We're going to have 0 to 1, 0 to 1, 0 to 1, and we've got 2xyz cubed. And let's just we'll do z first, then y, then x. That's kind of the classic order. All right, and so we're going to get z to the fourth over 4, 2xy, 0 to 1, y dx. This is going to be 1/2. Let's go ahead and move the 1/2 here out front. We plug in 1, we're going to get 1/4 times 2. That's the 1/2. And the xy just stay as they are. dy dx. And then we'll get 1/2, 0 to 1. The antiderivative for y is y squared over 2. Sticking the x in there, 0 to 1. Plugging in 1, you get 1/2. Move it out front, you get 1/4. 0 to 1, x dx. You get 1/4 times x squared over 2. 0 to 1. It's another 1/2, and we get 1/8. That's the answer. All right, and so that's how you can go through and use the divergence theorem to calculate f dot ds. Calculate the divergence, and then just do the triple integral across the object with the divergence as your functions inside of here. Let's go through and do another one so you can see it a second time. So instructions are the same. Find f dot ds. So we've got f equals xy plus 2xz I, and then plus x squared plus y squared j, and plus xy minus z squared k. All right, and then what is our object? S is the surface bounded by the cylinder x squared plus y squared equals 4, and the planes z equals 0 and z equals y plus 2. All right, and so it's helpful to draw yourself a little picture. We've got the cylinder, radius 2, 1, 2, 1, 2, 1, 2, 1, 2. All right, and then we've got z equals 0, that's the xy plane, so that's the bottom. And then z equals y plus 2, that's going to give us the top. And you can go through and pop some y values in. And again, I'm saying again because this is a similar problem from a previous video. If you go through and you don't have x here, that means you could just go through and draw this as a line and extend it in the x direction. And I would go ahead and just draw that line at x equals 0. And so if you go through and plug in y equals 0, you're going to get z equals 2. That's there. If you then go through and say plug in z equals negative 2, if you go through and plug in y equals negative 2, then you're going to get z equals 0. And if you plug in y equals positive 2, you're going to get z equals 4. And so we could go through and end up getting points for our plane here, here, and here. And if you extend this point, you extend this in the x direction, right? Since there's no x value, it's kind of like a cylinder. Extend in the x direction, you're going to hit here, you're going to hit here. And so we can go through and draw that piece in, and that represents the top for our surface. So you can kind of see the top from this plane z equals y plus 2 by doing it that way. Okay, so in terms of doing the triple integral, first we need to calculate the divergence. Derivative with respect to x there, so we're going to get y from that, and then 2z from that. Here we're taking the derivative with respect to y, that's 2y. And then here the derivative with respect to z, that's minus 2z, and the z's end up canceling and we end up getting 3y. So our triple integral is 3y dv over our object E. Okay, so you gotta recall how to go through and evaluate triple integrals. With triple integrals, I recommend you kind of compartmentalize. So I would recommend that you go through and think about doing the first integral and then handle the rest later. So if you have a nicely defined surface where z is by itself like this, then it's, they're kind of giving away what your order of integration should be by giving you z equals 0 and z equals y plus 2. They've nicely defined the bottom. They've nicely defined the top of the surface. And so I would go through and I would do dz first and do z from 0 to y plus 2. And then you can go through and do a and d separate, right? And so when you do those values, the second set, you're integrating across the domain for x and y, That's going to be the, the kind of the bottom of the object here. All right, so what would we get for those bounds when we actually did that? And you could go through and do this integral first and then do that. You could really separate them all the way. But I'm going to go ahead and just set up the entire integral. So we're going to have 3y dz. All right, and then when we go through and do the inner integral here, we're going to, since it's we have a circle, we're going to do polar coordinates. So r dr d theta, and then we'll integrate from 0 to 2. And why 0 to 2? That's because that's the radius for our circle, and then 0 to 2 pi. Okay, now the only problem with this is that notice how many variables we've got: z, r, theta, y. So there's one variable too many. So we need to go through and translate that y. And the way that you can do that is you can use your translation formulas for, since we're using polar coordinates, you can use your translation formulas from rectangular to polar coordinates. X is r cosine theta, y is r sine theta, and then x squared plus y squared equals r squared. And so we can replace y here with r sine theta. And so we're going to have 3r squared sine theta dz dr d theta. And then we have integral from 0. And now y plus 2, we're going to replace that with r sine theta plus 2. Maybe it would have been easier to do the first integral and then do the second set of bounds, but that's okay. And so now we've got everything set up, and we've got all, we only have 3 variables, z, r, and theta. And so we're good to actually do our integral now. So 0 to 2 pi, 0 to 2, 0 to r sine theta plus 2, 3 r squared sine theta dz dr d theta. Did we get that? Did we get all that right? 0 to 2 pi, 0 to 2, r sine theta plus 2. Okay. 3r squared sine. 3r squared sine. Oh, looks good. All right. So our first set of integral, we want to integrate with respect to z. There's no z here. We treat all this stuff as a constant. So the antiderivative is just of dz is just going to be z. So we'll have 3r squared sine theta z, 0 to r sine theta plus 2 dr d theta, 0 to 2 pi, 0 to 2, 3r squared sine theta times r sine theta plus 2 dr d theta, 0 to 2 pi, 0 to 2. You can multiply this. We're going to get 3r cubed sine squared theta plus 6r squared sine theta dr d theta. We can go through and integrate 0 to 2 pi. Here we're going to get 3/4 r to the 4th sine squared theta plus, what was that going to say? So we've got 6 r squared over r to the 3rd over 3. So we're going to have 2 r to the 3rd sine theta evaluated from 0 to 2 d theta. And we can go through and plug in. So we've got 2. So 2 to the 4th is going to be 16. 16 times 3/4. So we're going to get 12 sine squared theta. And then here we're going to get, what is this? This is going to be 8 times 2. It's going to be 16 sine theta d theta. And then to do this sine squared, we need to use the double angle identity. 1 minus cosine 2 theta over 2. This guy is fine. And then 0 to 2 pi. You could reduce this. This is 6. So we're going to get 6 minus 6 cosine 2 theta plus 16 sine theta. So the antiderivative here, we're going to have 6 theta The antiderivative for this one's going to be -6 cos 2 theta over 2, and then -16 cosine theta, 0 to 2 pi. So for this guy and this guy, these are both just going to cancel out when you plug in the 2 pi. If you take cosine of 4 pi minus cosine of 0 is going to be 0. Cosine of 2 pi minus cosine of 0 is going to be 0. And so we're just going to get 12 pi. Okay. And so that is the divergence theorem. If you've gone through and watched the Green's and Stokes theorem, the divergence theorem is arguably the easiest to go through and utilize, at least in the direction that we did. It's generally relatively easy to go through and find the divergence of a function, and then you're really just finding a triple integral. Certainly much easier to find the divergence of a function than it is to go through and find the curl, for example. And so that's the divergence theorem. All right, that's it. Thank you for watching. This is the last video for the multivariable calculus course. Hopefully these videos proved useful. Take care.